Hello Year 10, welcome to another lesson. Today we're going to be looking at electrical resistance. So hopefully you've put everything away and you're ready to focus on this lesson. You will need the mastery book because as we go through, mastery document that's on your Teams. As we go through this lesson, I will be referring to some of the questions in there that you might want to go and do as we're going. Okay, so let's start off with some learning objectives. So we need to be able to define electrical resistance. We need to know the connection between V, I and R, where R is electrical resistance. We'll come across that in a moment. And finally, we need to be describing how R of a circuit, the total resistance of a circuit, changes when we have series and parallel circuits. So resistance is a measurement of how much potential difference is needed to push 1 ampere of current through a component. So in other words, if I've got a resistor and I want to push 1 ampere of current through it, then I will need to have, let's say this resistor is 20 ohms, which we'll come to in a minute, then I will need to have 20 volts across it. So resistance is a measurement of how much potential difference is needed to push 1 ampere of current through a component. So as you can see here, the bigger the resistance, the more potential difference you're going to need. So what does resistance kind of look like? So here's a model for you to try and understand it. So here we've got two different wires or models of wires. The one on the right is a higher resistance than the one on the left, and we can see this because there are more of these pins that are going to stop the marbles coming down. Now the rate of the number of marbles flowing down through this is going to be our current. So let's see what happens when we let the marbles move. So the marbles on the left hand side here are moving a lot quicker than the marbles on the right hand side, and the marbles on the right hand side are slowing because they are hitting atoms as they're going through that wire. So they would need more push to get through there at the same rate as the marbles on the left hand side. Okay, so this is the idea as to what resistance is. So the greater the resistor, or the resistance, doesn't have to be a resistor, the lower the current. So as R goes up, then I must go down. So let's do the opposite. So the lower the resistance, the greater the current. And that's because, as we've seen before, it's easier to get through get the electrons through the wire, which means that the current must be bigger. Let's just have a look at this in terms of an animation. So here we have got a circuit, we have got a source of potential difference, a single battery, we've got an ammeter, and we've got a resistor. Now, if I click on the resistor, I can see its resistance. So when the resistor has 10 ohms, there's 2 amperes of current flowing through. And notice we're not going to change the battery here at all. And if I increase my resistor to, let's get to 40 ohms. If my resistor goes to 40 ohms, then my current drops to 0.5 amperes. If my resistor goes down to 5 ohms, then my resistor increases to 4 amperes. So the greater the resistance, the lower the current, and the lower the resistance, the greater the current. So resistance is the PD, so it's the potential difference needed per, and we'll talk about per in a second because it's quite an important way of describing in physics. So it's the PD needed per ampere of current to flow. Now, why have I made a big deal out of per here? Well, per in mathematical terms means divide. Okay, and it also, you can see it as a slash. Okay, so we've looked at it before, but meters per second means distance divided by time. In this case, we're looking at PD, which is V, and ampere of current, which is I. So we can say our equation is going to be resistance, R, is equal to potential difference, V, per current, I. So you can see that we built our equation by using that word per. We can define our letters as well, so let's make sure we do that. So V is the potential difference, and we know that that's measured in volts. I is the current, and that is measured in amperes. And R is the resistance, and that is measured in this new unit, looks a bit like a horseshoe, called ohms. And I shall draw that a bit bigger for you now so you can see. So there's our equation, really important equation. We measure resistance in ohms, OHMS, and the symbol is a Greek letter omega, which is a big kind of horseshoe shape. So we know that R is equal to potential difference divided by current. So we could rearrange this, and you're more likely to see it looking in this style. If we rearrange it for V, that means we're going to multiply both sides by I. So we'll multiply that side by I, we'll multiply that side by I, so we'll be left with V on its own is equal to I times R, and this equation, V equals I times R, is probably how you'll see it, because this is also known as Ohm's Law. So quite an important equation to use. So we're going to do 3 examples now to make sure you can see how to do them. These examples are exactly the same as the ones in your mastery booklet. So compare them, go through them, make sure they make sense. As always, if there are any questions, you know how to contact us. So let's start with example 1. I would like us to calculate the resistance of a component when a potential difference, a PD, of 20 volts gives a current of 0.5 amperes. Okay, so first of all, as we've always been doing, we write down what we know. We know V is 20 volts. We know I is 0.5 amps. But we don't know R, so we're going to need to work R out. So R is equal to V over I, because it's the current divided by, it's the potential difference divided by the current. It's the volts per ampere. So we've got 20 divided by 0.5, which will give us an answer of 40 ohms. So that's the first kind of question we can have. Let's have a look at another example. So question 2, we're going to look at a different type of question now. So this time I want to calculate the current when the potential difference is 40 volts. Is 40 volts, and the resistance of our component is 2 ohms. So as always, let's write down what we know. We know the potential difference, it's 40 volts. We don't know the current. We do know the resistance, which is 2 ohms. So this time we'll start with V equals I times R. Going to want I on its own. So in order to have I on its own, I need to divide both sides by R, because whatever I do to one side, I must do to the other side. So therefore, I'm going to have V over R is going to be equal to I. Now we can put our numbers in. So that's going to be 40 divided by 2, and then 40 divided by 2, we know, is 20 amperes. So there's example 2. So we've looked at resistance, we've looked at current. Example 3, let's see if we can calculate the potential difference. So example 3 is going to be calculate V when, also calculate the potential difference. So the PD required to have a current of 2 amperes flowing through a 4 ohm resistor. Okay, so what do we know? We know current is 2 amps. We don't know potential difference because that's what we're asked to do. We do know resistance is 4 ohms. So we'll start with our equation. V equals I times R. Oh, don't need to do anything with it, so that makes life quite easy. 2 times 4, we'll substitute in. 2 times 4 is 8, so we have 8 volts. Okay, this would be the perfect time to pause this YouTube video and have a go at those first few questions where there are some calculation questions. Make sure you can do them. We'll be putting up the answers next time. Follow exactly the process that I've just gone through there. Okay, well done, ladies and gentlemen. Hopefully you have managed to do those questions. Just a little bit more of theory today, and then you can go and have a go at the virtual practical. So we're going to quickly talk about resistors in series and resistors in parallel. So those two different types of circuits that we've looked at before. So when we have resistors in series, we will have resistors one after another. So if we want to add another resistor, we just add it in series. So it would go one, and then the next, and then the next, and so on and so on. When we have resistors in parallel, we will put a resistor that can be in series within a branch, but for our sakes, we're going to put them across different branches. So it might be that this is a 5 ohm resistor, and this is a 10 ohm resistor. And this one might be a 5 ohm resistor, and this one might be a 10 ohm resistor. So, same resistors, might have a few more wires in here, but same resistors, same circuit. The idea is that we have 2 resistors in series, and we have the same 2 resistors in parallel. So, resistors in series. When we put them in series, what we're actually doing is we're causing the total resistance to increase. So the total resistance of this circuit is increased. Compared to what is an interesting question, but it's increased. If I put a 5 on its own and I put a 5 and a 10 together, then it has increased. So the current will decrease by a large amount. Because the resistance has increased. So as the resistance goes up, as we looked at previously, the current goes down. Now if we look at the parallel one though, still got the same 2 resistors, but this time it's one on a separate branch to the other one. So there's actually 2 routes round now for my current to go. I've got the green route, which might be going round there and then back. And I've also got the blue route, which is going that way, going around there, and then back. So two different journeys for those electrons to go. And as we know, when we go parallel, we're actually allowing a greater current to flow because these extra wires have also got more electrons inside of them. So in this case, the total resistance of the circuit has actually decreased. So you can think that there's a second route for our electrons to travel. So it's decreased compared to the series. So this has a lower total resistance than this one here. And that is because there are more paths for the electrons to travel through or travel down. Okay, so the electrons can go either through the green route or the blue route, and each way they go, there are electrons kind of splitting, or the flow of current is splitting at the two junctions, which means you've got some electrons going this way, some electrons going this way, but they're only seeing a 5 ohm resistor and they're only seeing a 10 ohm resistor, so they're not seeing that total of 15 ohms that they do in series. So parallel has a lower total resistance than series, and that's really important. We don't go into it any more depth than that, but that's really important to see. So let's just go and have a look at the simulator to see this in action. So here we have got a series circuit. There is a 10 ohm resistor and a 5 ohm resistor, opposite way around to what we had on our diagram, but it's still the same. And we can see here we've got a current of 0.6 amps when we've got a voltage of 9 volts across them. If I go across now to a parallel circuit, we've still got a 10 ohm and a 5 ohm, and we've still got a 9 volt source of potential difference, but we see the total current is a lot higher. It's 2.7 amps compared to the 0.6 amps on here. So that means the total resistance of this circuit must be lower than the total resistance of this circuit because more electrons are able to get through. And in fact, you can see here with the separate currents that more electrons are traveling through this second circuit because this is the lower resistance resistor. Okay, so that is what we're seeing when we talk about the difference between the two. In series, those resistors, the electrons have got to go through both of them, so that means that they need to sort of share their energy from the battery, which means that they're going to be quite slow. In parallel, they can use all their energy to get through this first resistor, or they can use all their energy to get through the second resistor, which means when they come back through to the battery, they've got a much higher current, which means they have a much higher resistance, much lower resistance, sorry. Okay, so we're going to go on to a few more little bits now just to end this session off. Let's go back to the visualizer. So here we've got a circuit. We've got a 10 ohm resistor and a 5 ohm resistor, just like we've seen on our circuit construction kit there. And we've got a 9 volt cell that's putting that potential difference into the circuit. Now, as we've seen in those previous lessons, we know that the potential difference that we're getting from the battery is being used up across any components in the circuit, especially when we're in series. So here that 9 volts has to be shared between the 10 ohm and the 5 ohm resistor. Now, because that 10 ohm resistor is a greater resistance than the 5 ohm resistor, it actually gets a bigger share of the potential difference. So a bigger resistor in series has a larger potential or larger portion of the potential difference. Now, you don't need to be able to work this out until A level. This comes back at A level. But what you do need to know is that if you have a larger resistor, you will have a larger potential difference. So a bigger R in series has a larger portion of potential difference than a smaller resistance. That's all you need to know. But that's because you've got, if we go back to thinking about that animation from the beginning, it's got more things stopping it, more atoms stopping it, so therefore it's harder to get through, so you need more energy to push them through. So that 10 ohm resistor needs more energy than that 5 ohm resistor. In fact, because it's double the resistance, it needs double the energy, and that's how we work this out. But like I say, that comes back at A level, so don't worry too much about that right now. Okay, the final thing we need to do, and this is quite a big important part because this will come back certainly in an exam, is how to measure resistance. So measuring the resistance of an unknown component. So something we don't know what the resistance is and we want to work it out. So the first thing we would do is we would have our source of potential difference, our cell or our battery. We would have a variable resistor, and that's a resistor we can change the resistance of. It can go high, it can go low, but that variable resistor is really important. We'll then have an ammeter in our circuit because we need to measure the current. There's two things we need to know to work out resistance, and that is current and potential difference. And we'll have our unknown component, which we're just going to make be a resistor right now, but obviously it could be anything else. What we haven't worked out yet, well, what we can't measure, we can measure the current, but we haven't got anything to measure the potential difference. So we'll put a voltmeter in parallel over our component we want to measure. So now we've got our current and we've got our potential, we've got our voltmeter, which will measure our potential difference. We can measure the current, we can measure the potential difference. And that's what we need in order to get back to R equals V over I, which is what we started today's lesson with. So that bit of information, R equals V over I, is actually really important because it tells us what we need to be able to measure that resistance. So what do we do? Well, first step is we vary the variable resistor. Okay, and once we've varied it, we're going to take our ammeter reading and voltmeter reading. And then once we've done that, we're going to vary it again. So we'll go back to step one, vary it again. So we've got a different part of our potential difference being used just to get over our resistor before we get around to this point here. So we're going to vary it again, which then we're going to take our ammeter and our voltmeter reading. And we'll keep doing that until we've got 10, 20, 50, 100, depends how accurate you want to be, readings. And then we can either calculate it or we can draw ourselves a graph, which will come in a later lesson. We put our potential difference along the x-axis, current along the y-axis, and we'll get a nice straight line. And that will come back to in the future. So, what have we covered today? Well, let's go back to our statements at the beginning. What is electrical resistance? Well, electrical resistance is a property of a component that is trying to reduce the amount of current that flows through, and it's a measurement of how much potential difference we need per ampere of current. So we know that R is equal to V over I, coming back to this part here. So the connection between V, I and R, as we just said, is R equals V over I, or if we want Ohm's law, V equals I times R. And what are the different effects of adding resistors in series and parallel? Well, in series, the total resistance is increasing because the electrons have to get through both of those resistors, and in parallel, the total resistance decreases because we have two or more different branches for those electrons to flow through. Okay, so that's the fundamentals of this lesson. What I just want to do now is to talk you through how you're going to do the virtual lab. So you're going to go back to the FET website that we've used before. Let me just clear this so we can see. You're going to take a battery. Remember that if they're red, these circles, that means you haven't connected it. So it's really important to make sure that you're connecting so that those circles go black. If you see a red circle, you haven't set up your circuit correctly. you are going to have a resistor very near to the battery, because this is going to be your variable resistor, which you can change by clicking on it or tapping on it and moving the dial up and down, as you can see here. You're then going to make sure you have got a second resistor, and you're not going to look at what the value of this resistor is, unless you want to cheat, until you have done the experiment. Oh, I know what we've forgotten. So if you click on it, you can delete what you haven't put in. We need an ammeter, so we'll rotate that ammeter and we'll put that in series as well. And finally, let's finish the circuit. So our resistance is quite high, so let's put it quite low. We'll go for 2 ohms to start off with. We're not going to record that resistance. What we're interested in is the potential difference across our resistor. So let's set our 2 probes up here. So we've got 7.5 volts going across it, and I've got a 0.75 amp current flowing through. We'll then click on this, so record those down in your table, change the resistance, so now we've got 4 ohms over here. I've got 6.43 volts going through my resistor and 0.64 amps going through my ammeter. And we'll keep changing it. We'll keep changing it, so we've got quite a few bits of data. So 5.62 and 0.56, etc, 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 until you get to somewhere around sort of 50 ohms. Doesn't matter if you get that far, but just try and have 10, maybe 15 sets of data that you can do. Now you can record all this data on the mastery sheet, and then I would love for you please to write me a conclusion which explains what you found out. What is the resistance? Did it agree with the resistance of a resistor? Remember, if you click on a resistor, it will tell you what the resistance is. So click on this resistor when you're at the end. Did you manage to calculate it? And don't forget to calculate the resistances of each of your sets of readings by doing the potential difference divided by the current. As always, if you've got any questions, you know where to contact me. Contact me using the science email address. We'll get back to you. We check that twice a day, so we'll get back to you as soon as possible and it help you with any problems you've got. Give it a good go, ladies and gentlemen. Have a real go at the virtual labs. It's really worthwhile doing. Obviously, we would do this with real labs in the classroom, but this is just as good because electricity is really good to do on a computer. As I say, any problems, contact me via email. Okay, thank you very much.